In this webcast, we're going to focus on the center of mass and radii of gyration, or in some sense a rotational center of mass. The idea is, in order to calculate the center of mass, if you've got an object and you want to find its center of mass, we'll just look at the center of mass in the x direction. The idea is, if you were to calculate the distance times by the mass of each piece, so you take each point in the surface and take its distance and multiply by the mass, you will get what is called a first moment of mass. If you add all of those up, you will get, in some sense, the combined first moment of mass. You're adding up a bunch of moments. This quantity right here can also be thought of as if you were to take the varying x's, notice the x values differ, and replace each of the x value with a constant. So in some sense, take every point and compress it, push each point back so that it all lies on the same exact x value. Then if you were to calculate the moments, you should get the same thing regardless of how you do the computation, with the varying or with the constant x value. This x value is called your center of mass. It's where should all the mass be placed to obtain the same moment. Well, this is a constant, so it can be pulled out of the integral. And then over here, I still have my integrate x dm. I now solve for x bar, which gives me integral of x dm over dm. That right there is our average value formula for x bar, and it just gives an alternate way of viewing it. The reason we study this alternate way is it's what we're going to do now to study rotational center of mass. What if instead we have an object that we are rotating? And we've got some object and we're going to start rotating it. Well, is it possible to put all of the object's mass at a specific radius? So I've got an object, and I'm going to take the object, and I would like to compress it all so that it's at some set radius. So take the points that are close, push them out, take the points that are far out, compress them in, so that you're taking the entire mass and compressing it to be at one specific radius. That radius right there is called the radius of gyration. And the idea is, when we're calculating rotational things, we look at moments of inertia. Rather than a moment of mass, we're looking at a moment of inertia. So I need a radius, and inertia, remember, is you're adding up the varying radii squared with respect to mass. Well, the radii are varying. What if I replace the varying radii with a fixed, constant radius? And that constant radius would be this big R, which doesn't change. What should it be so that I end up with the same inertia? Well, since it's a constant, I can pull it out. And on the left-hand side, I have inertia. On the right-hand side, if I add up little bits of mass, I'm just getting mass, which means I can solve for R by writing I over m and taking its square root to give me my radius of gyration. That's how you get a radius of gyration. Now let's look at an example. Let's suppose we are on a helix, and I need a density. So in this case, let's just make the density constant. We'll go around the helix once, and we'll have our density be a constant. In order to calculate these integrals, one of the things I need is I need an r prime. So that's a negative sine t, cosine t, 1. I also need the speed, which is the square root of sine squared plus cosine squared is 1 plus 1, giving me a root 2. If I want a little bit of mass, which is the term that shows up in here, I need density times a little bit of length, which is density times speed times dt. The density is 3, the speed is root 2, and this is now my dm quantity. So if I'm going to do a moment of inertia, or if I'm going to find the moment of inertia about the y-axis, remember the distance to the y-axis. Well, if we're in 3D, we need to get distance to the y-axis. So I want distance to this axis. If I've got a point in space, and I want that distance right there, I need to know z, I need to know x, and the distance to the y-axis is x squared plus z squared, square rooted. So I'm going to integrate the radius, x squared plus z squared, squared. Take square root and square it with dm. Notice the squared and the square roots cancel. Now, if I'm going to go around the curve once, I got to go from 0 to 2 pi. I now need the x value. The x value is cosine t. I also need a z value, which is t. And then I need to multiply by dm. dm is 3 root 2 dt. That is my moment of inertia about the y-axis. If I'd like the radius of gyration about the y-axis, then that's take the square root of I over m. Well, I already know what the I is. The I sub y is this quantity, 0 to 2 pi cosine squared t plus t squared, 3 root 2 dt. Now I need to divide by mass, but to get mass is found by adding up little bits of mass. So I add up little bits of mass. And that right there gives me a formula which will calculate the radius of gyration about the y-axis. And that